Hi everyone. So in this video, I'm going to be showing you the geo clustering app that I've just created. So just to give you some context, this is created in the wake of a lot of talk around geo holdout tests. Holdout tests are basically required for carrying out incrementality tests. So you want to understand which campaigns, which strategies, or sometimes even which channels are actually giving you the most incremental returns. So in order to do that, you just pause or withhold uh, running ads or your campaigns in certain regions. This entire concept is called a holdout. So you basically have two groups of geos in such tests, in such scenarios. One is called the control group and another is called the test group. So how do you decide on those geos? Suppose you're running in United States, your campaigns, your brand is running its ads in the United States. So which of the states in the USA would you want to hold out, and which of the states would you want to sort of show the ads in? This is the question that is this particular app is going to try and answer. So it's going to give you that opportunity to use a scientific methodology instead of just going after random. And by random, certainly don't mean the statistical concept of randomness, but just a guesswork basically. Just trying to guess, okay, which of these geos should we select. So there's actually a logic, and the most important assumption of a geo holdout test is that the geos in the control and the test groups must be nearly identical. Now we all know in real life no two geos are really identical, but they can be very similar in certain aspects. So in this case, as you see in front of you, the geoclustering app has been created using Streamlit, and this is the state here, and I'll just show you the data points here. So all you have to do is basically browse files, and you have to upload a CSV file. And in this particular configuration, currently the app is in this configuration where you have to upload in the form of state name, revenue, orders, and AOV. And you see that these are basically the criteria for clustering. Now you can easily add more features. You can add more ways to understand what is the best way to classify between control and test groups, and most importantly, not classify between control and test groups, sorry, but to sort of cluster them together based on these parameters. So what more features could you classify the different geos into? And once you have done that, once you actually have clusters within each cluster, you can choose any set of geos as control and test. That's the whole idea. So there is within cluster homogeneity, there is across cluster heterogeneity. So the algorithm that's working at the back end is called k-means clustering. It's a machine learning language. It's a machine learning model, or algorithm rather, and it works on a very simple and intuitive principle. You simply provide first the algorithm, the number of clusters you want. So for instance, you'll see that I've gone on to give 4. So it could be k equal to 3. A very common, so the k, by the way, in k-means clustering is the number of clusters. A very common choice is k equal to 3. But in this case, I went with k equal to 4. I'll just show in a moment why. So you first provide the number of clusters, then the algorithm is going to randomly select certain points for the centroids or the centers of different clusters, and then all the points will be around it, and then the objective of it will be to bring all the points to the cluster which is the centroid of which is nearest to the point. So each point will be assigned accordingly. So essentially what moves is not the points but the centroids. So the centroids move around, and this process keeps repeating until each point is in a cluster where the centroid is closest to it. So every point is therefore, and therefore every cluster rather is extremely coherent, and it's the most optimal mix. And most of the points are in the cluster whose centroid is closest to it. So it's ultimately a concept of distance, which is common in algorithms. So it basically reduces the distance based on these features. So the distance is calculated on the basis of the features that you have provided the algorithm in the data set. So in this case, I've gone with performance, historical performance of historical data, number of revenue, orders, or AOV from each of the different states. So you are seeing just a preview of the data set, and of course this consists of all the states. And you will see that this is basically a cluster validation. So cluster validation is giving you a couple of metrics, the lattice score and Davis-Bouldin index. Now, what these two do basically is give you an indication of what is the optimal number of clusters. So for Scenario score, it's the higher the score, the better it is. So you'll see that k equal to 3 is actually a very optimal number. But here the question is, like I said, of course, you understand there's no k equal to 1, right? It makes no sense because you're not doing anything at all. It's just one aggregate data set. It's only from k equal to 2 that you're starting doing clustering. So at k equal to 3, the Scenario score is actually the highest, but I've chosen 4. And the reason why is actually from the business logic and by looking at the data set, and just come to that in a moment. For the Davis-Bouldin index, it actually is just the opposite. The higher is the score. The lower is the score, the better it is. So you'll see that as the number of clusters increases, the score is actually becoming higher. In this case, it's the opposite. As the clusters increase, the Scenario score is decreasing. So there is an optimal point, and you can use these to validate the number of clusters in your case. But this is just one way of validating it. So this app also gives you the Scenario score and the absolute values of these two indexes. But you also actually have to look at the clustering plot. This is a nice visual way of looking at how the clusters really look like, the geo clusters that is. And this is with respect to 2. So this obviously will be a 2D plotting. And I have also shown a 3D plotting after this. So this is with AOV and revenue. And this is with the revenue, AOV here in this axis, and you also have orders here. And seeing the 3D plot, you see a very similar picture arising as is here. So there are 2 here, there's another one here, there's another one here, and there's another. So if it were k equal to 3, I also did that iteration. And I saw that this entire section here, this purple, I think this is a purple color, and so the purple ones and the yellow ones, they were sort of clubbed together into one cluster. And I thought that's probably not the best idea because these here represent slightly higher revenue. Or not slightly, from slightly to quite a bit of higher revenue. So this deserves to be in its own cluster. And therefore I thought that I would increase it to k equal to 4, even though the clustering validation metrics here actually show that k equal to 3 is the most optimal. So you have to still use your business logic or your understanding of the situation. The data and the analysis is only going to do so much. You will still have to apply some sort of common sense in order to make the best decisions out of it. So once this has been done, you will basically get 4 clusters, right? So you have the 2D and the 3D plots for a nice visual idea. You can understand what each cluster stands for, where they really, why they are as they are. So for instance, these two have much lower revenue, but they have high AOVs, and the number of orders is actually also relatively on the lower side, because this is the axis, right, from here to here. So this is actually just a couple of outliers, to be honest, and that's why it has formed its own cluster. And there are some blue points here. There are some states which are, pretty decent in terms of revenue and orders, but not as high on the AOV. So you'll see that across the board, there are not too many which are of high AOV. So that's not unusual. In this case, pretty much there's a flat AOV actually across the brand. So that's why it's not unusual for this particular case. And for the actual outcome, this is of course a visualization, but you ultimately need the names of the states, and this is where you actually get the names of the states. This is where a table gets formed. We can download it from here. This simple download as CSV, and you get the names of the clusters. You will see that there are 2 clusters which primarily contain most of these. By the way, there are also in this data set some cases where it says that it's not valid, and it probably also says that it's not informed. I think there's another one. So there are some use cases like that which have also been included in this data set. But yeah, so there you go. There's another one here, not informed. But the point is that it consists of all the states and it has been clustered. So if you want to choose now control and geo groups for carrying out your geo holdout test, so you can choose some from here, maybe 3 or 4 from this cluster and 3 or 4 from the same cluster. So you have to choose from the same cluster because they share or they have the shared characteristics which make them part of the same cluster. If you choose across clusters, then it kind of defeats the whole purpose. So that's the whole point. You also have the download cluster table as CSV here, right at the bottom. Very simple app. This runs on Streamlit Community Cloud, and I will share the link in the description. So yeah, if you have any questions regarding using it, right now the format is this. So this is a required format. These have to be the names of the columns. State revenue orders in AOV. If you require it in any other format, if you need more features to be added, or any other kind of visualization or anything else at all in the output, do let me know. I can help you get a more customized format of this. So hope this was helpful. If you have any questions, let me know in the comments. And thanks for watching. See you in the next video.